On behalf of Indian Aerosol Science and Technology Association, I welcome all participants who are present here to attend 7th lecture of IASTA monthly online lecture series. IASTA is running this series successfully, bringing best researchers to give lectures and share their valuable insights and expertise with the interested ones. Today we have with us another distinguished aerosol researcher who has kindly agreed to give her time to benefit all of us. As she remarked just now, we met recently during Indian Clean Air Summit at Bangalore, and I am sure that AAAR and IASTA will find ways to connect in more and more directions and do better and better for the aerosol community. Our today's expert is Dr. Faye McNeill from Columbia University, and I request Dr. Neeraj Rastogi to kindly introduce her to our participants. Dr. Neeraj, please.
Okay, thank you, Dr. Joshi. So it is indeed my great pleasure to introduce today's speaker, who actually doesn't need any introduction for the aerosol community. She is well known. But for the sake of completeness, let me introduce her. So Dr. Faye McNeill is a professor and vice chair in the Department of Chemical Engineering and a professor in Department of Art and Environmental Sciences at Columbia University, New York, USA. She is also an associate member of Earth Institute faculty and principal investigator of the Columbia University Clean Air Toolbox for Cities initiative. She joined Columbia in 2007 and received tenure in 2014. She received BS in Chemical Engineering from Caltech in 1999 and PhD in Chemical Engineering from MIT in 2005, where she was NASA Earth System Science Fellow. From 2005 to 2007, she was a postdoctoral scholar at the University of Washington, Department of Earth and Atmospheric Science, Department of Atmospheric Sciences. She has received numerous awards because of her outstanding research. To name a few, she received the NSF Carrier and the ACS Petroleum Research Fund Doctoral New Investigator Award in 2009. She was the recipient of Kenneth T. Whitby Award for the American Association for Aerosol Research in 2015. And Mellon Champ Emerging Leadership Lectureship at UCSB in 2018. She was named Fellow of Royal Society of Chemistry in this year, 2023. She is the Associate Editor in charge for Atmospheric Chemistry for ACS Earth and Space Chemistry Journal. She was a co-editor of Atmospheric Chemistry and Physics from 2007 to 2017. She has served in multiple elected officer positions in AICHE, AAAR, and AGU. She is the current president of AAAR for the year 2003-24. She is an appointed member of IUPAC panel on kinetic data evaluation and the ACS Committee on Environmental Improvement. There are many things to tell, but because of time limitation, I will not tell many things. And she will be talking about atmospheric aerosol chemistry and how it is bridging the molecular to urban to global scale. So with these few words, I invite Professor McNeill to deliver her talk. Professor McNeill.
Hey, thank you so much for that kind introduction and for the opportunity to speak today. This is a good idea, this lecture series, and I'm very pleased to be able to participate in it. I want to apologize. My background is a little messy because we just moved our flat last week. So a lot of exciting things are happening. But I'm at home in New York at the moment. All right, so let's go ahead and get started. I also wanted to say, wishing my best on behalf of AAAR to IASTA. I think that there are a lot of interesting opportunities for the two organizations to interact and benefit from one another. So I'm glad to continue to have contact with IASTA. All right, so let me get started. Okay, so I think that everyone here is aware that air pollution is a threat to life around the world, especially in many of the most populated parts of the world. So this image you may have seen before was created by the Health Effects Institute, researchers there. And, it's kind of showing a heat map of PM 2.5's fine particulate matter concentrations around the world. And we can see that in many of the most populated parts of the world and in many of the places that might not have resources to tackle the problem. PM 2.5 air pollution has reached crisis levels and is threatening public health. Of course, the second question you might ask is, where did this data come from, right? Because if we were to also look at coverage of PM 2.5 measurements across the world, many of these places are the same places where there's a huge data gap. So, across Africa, for example, it's an interesting question that often the places where the problem is most intense, we need to fill in some knowledge and data gaps in order to be able to make the first steps towards progress. So this will be a theme I pick up on later in my talk. So specifically, I know many of you are in India, most of you are in India watching this talk. If you're in North India, this doesn't come to any surprise to you that PM 2.5 air pollution reduces life expectancy where you are. So, particularly in the wintertime in the Indo-Gangetic Plain, there are very high loadings of PM 2.5, which are affecting public health. But even in the south, places like Chennai, which are normally thought of as being quite clean and don't suffer as severe of a problem, there's an impact on life expectancy of up to 2 years. So there's been a huge amount of progress towards cleaner air in India, I would say in the last 7 or 8 years, but there's still more to be done. So, it's important to understand, and I don't think I have to tell a group of aerosol scientists this, but, just to be clear, it's not a simple problem or else we would have solved it already in most places, right? So the air pollution that we observe and the PM 2.5 levels that we observe are, they do originate with emissions, both from human activities and natural sources. But then there's this kind of complex machinery or transfer function that exists in the atmosphere that involves a lot of nonlinear processes that are not completely known, including, gas and particle phase photochemistry, meteorological factors, multi-phase chemistry, including in the cloud water and in the aerosol, thermodynamics, et cetera. And these things connect the emissions to what we eventually observe. It's not as simple as seeing, some highly emitting local source and nipping that in the bud, and then we'll solve the entire problem all the time, even though that also is something that we should be doing. So, this kind of nonlinearity and complexity makes it difficult to know what the smartest strategies might be for cleaning up the air, right? What should we be investing in that will give us the most impact for the least, economic burden, I suppose. And there are also a lot of technical issues that I'll talk about today that involve, as we slowly start to unravel, what is this machinery connecting the emissions to air pollution, the system, the picture that we're building is extremely complex and in some ways not manageable for simple modeling purposes. And so we need to develop strategies to deal with that. In my group, Niraj mentioned that, I'm leading this Clean Air Toolbox for Cities initiative, which, we're focusing more on the on-the-ground issues. We're working directly with governments, making, measurements to fill data gaps, et cetera. And I'll talk towards the end of my my lecture on some work that we've done in Kolkata as part of this project. But the foundation of my group and what I've been doing since the beginning of my career is more on this side of fundamentals. In the McNeill lab, we do laboratory experiments, numerical modeling, and reaction mechanism engineering to try to better understand these atmospheric chemical processes. So, what do I mean when I say there's an issue of scale in atmospheric chemistry modeling? So, I started out as an experimentalist. I still am, but initially that was my main thing that I did. And when we do experiments in the laboratory, we're often unraveling processes that are happening in the atmosphere, but we're doing it essentially one molecule at a time, or just a few molecules at a time. And we're inferring important information, but we're adding more and more detail to our understanding of what's happening in the atmosphere. Meanwhile, at the other extreme, we have large-scale atmospheric chemistry and climate models, which are computationally constrained, right? So you can think of the extreme example of a climate model that the atmosphere is just one small part of that model. And then atmospheric chemistry is an even smaller part of that. And so for these things to run in any reasonable amount of time, they can carry at most maybe 100 chemical species total in the atmosphere, whether we're talking about gas or aerosol. Meanwhile, we know that an individual aerosol particle has more than 10,000 unique chemical compounds in just one particle, right? So it's the reality that the system is immensely complex, but that we have to simplify our representation of it for representation in the large scale models. And, we want these models to be as accurate as possible. And so we have to be systematic about how will we bridge this scale from the very high level of detail on the molecular level that it keeps increasing. More papers come out every day in the literature on these topics. And meanwhile, we want these large scale models to be accurate. So I've largely said this. So my group has done a lot of work thinking about this problem, specifically from my perspective as being an experimentalist. I certainly spent times, sitting in my desk thinking, oh, we discovered this really fascinating reaction. It's so fast. It really generates a lot of particulate matter. Why isn't it in the models yet, right? And my first thought was, it's because the modelers haven't read our paper yet. And that was true, but that was not the only reason why this information hadn't been included in the models yet. There are major technical issues to figuring out, what are the, which of all the hundreds of processes out there are important enough to dedicate computational resources to, and then, how do we represent them? So this is an example of things we've done through the years. So we've done this using a series of models that bridge that gap. So we use box model named named the gas aerosol model for mechanism analysis, GAMMA, which we developed more than 10 years ago at this point. And we use that to so what a box model would be if you took just one grid box of a large scale model and don't worry about transport in or out of the box. This allows you to include a lot more chemistry and phase mass transfer and these kinds of issues in the model. And therefore you can throw the whole kitchen sink of chemistry into these models, observe trends, infer kinetic information from laboratory data, and develop parameterizations where appropriate. And so we've spent a lot of time, and we still do, using that approach. Most recently, and what I'll tell you about now, is work that we've done towards automated model reduction. Okay, so the idea being that, let's say, even if your mechanism, even if we're just focusing on the gas phase, don't even worry about aerosols at the moment, many of the chemical mechanisms that we're dealing with are huge and complex, and we need to reduce these down to a manageable size. And what I was, I'm trained as a chemical engineer, and so I had some basic exposure to reaction mechanism engineering as a student. And I was really surprised to realize that in our community, for the most part, this is done by hand, right? This is done empirically. Maybe a postdoc will spend a few years, write down which species they think is important, and then tune to get the right parameters. This is what I mean when I say that the process is kind of artisanal, right? So there's a lot of care given into this process. And then by the time the model is reduced, nobody wants to change it because they've put so much effort into making this reduced model. So if we had a way of doing this in a more systematic way, so one that's kind of following a set of rules, following an algorithm, this could obviously make the model reduction faster. It could be more accurate because it would eliminate the room for human error, and it would reduce people's reluctance to update the model. It would be easier to update whenever new chemistry came out in the laboratory. So that's what this Amore project is about. So this project is funded by US EPA. They, of course, run their own large-scale air quality model, regional air quality model called CMAQ, which many of you may be familiar with. And so they're very interested in keeping, technology that would enable keeping the models up to date with the latest science in an efficient manner. And so the idea here is that, we are developing the algorithm Amore, which takes as inputs a full-scale complex mechanism, as well as the parameter space we're interested in, and any species which we would like to prioritize in the reduction. And then it outputs a reduced mechanism, which we can test both in box models and in the large-scale models that we're targeting. Okay. So I'll talk about the first generation of Amore, which this paper was published in January or February of 2023. So you can see it if you go online. So our goals for the algorithm development, and I should note, I think I have the author list here. So this is a very interdisciplinary project. It's led by my graduate student Forwood Weiser. He goes by the name of Woods. It's a collaboration with EPA. Havala and Brian was at EPA at the time, so they're CMAQ developers. We have a computer scientist who's a specialist in algorithms and graph theory. We have large-scale modelers specializing in geochem. And, we kind of all work together to design this algorithm and see this vision through. And I should say, I think it's been a really exciting collaboration, and very productive. So our goals when we set out was that we should be able to just supply the large-scale mechanism, which, of course, that includes the structure of the reaction network, as well as, the kinetic data associated with it. And with relatively minimal input from the user, no kind of expert knowledge needed. The algorithm should be able to produce a reduced mechanism. We, of course, had to start somewhere, so we started with isoprene as a test system, but the idea was to have it be general and be applicable to other complex networks. We said, I'm an engineer, so I'm practical. I said, unless this thing can make mechanisms that are as small as what's currently being used, for example, in CMAQ or geochem, nobody's going to use the reduced mechanisms that we generate. And so we need to be able to get as small and at least as accurate as those mechanisms. Let's say if we got equally small and accurate, we still would be providing an advantage in the sense that the reduction process is automated, and therefore that saves a lot of time and reduces barriers to updates, et cetera. But as it turns out, the automated process allowed us to get higher accuracy. So that was good. I'll show you the data in a moment. And we had lots of data to compare our model mechanisms with. So, of course, we can compare it to the full-scale mechanism. We can compare it to other mechanisms that are currently in use. But there's also physical data, experimental data, or field data that we can compare to. So definitely lots of testing happening. There's a question in the chat. Right, this is the publication. All right, so we started with isoprene as our example mechanism that we started with, okay? The reasons why we chose it: isoprene is the most abundant non-methane hydrocarbon in the atmosphere, and it's so abundant that its oxidation actually controls the level of oxidants in the atmosphere, right? So it titrates the oxidant levels in the troposphere. So if you don't have isoprene oxidation correct in your model, nothing else will be correct. On the other side, isoprene is a very important source of fine particulate matter, right? So SOA formation from isoprene oxidation products, in the last few decades has been discovered to be very critical for modeling air quality. In addition to those reasons why it's important, the mechanism is also very large and complex, and our understanding of it continues to expand day by day. So here's an example of the mechanisms that are out there. So the master chemical mechanism says that the isoprene oxidation mechanism has over 600 species in it and almost 2,000 reactions. Okay. Paul Wenberg and coworkers compiled an expanded mechanism in 2018, which we refer to as the Caltech mechanism. They did this through a very thorough review of all of the experimental data and theoretical data that were available. Their mechanism is slightly smaller, but still very large. And then on the other end, there are the isoprene oxidation mechanisms that are actually used in large-scale models. So the RACM2 and CB6R3 are two isoprene mechanisms that are used in CMAC. Okay, so we're going from 600 species down to around 10. This Caltech Reduce Plus mechanism is what's used in geochem. So this is something a little bit intermediate in size. Okay, so this is, the challenge that we have. Okay, so the reference mechanism that we used, as I mentioned, it was based on the Wenberg mechanism, but we had to expand it a little bit because since Wenberg based his mechanism on known experimental and theoretical information, it was a little bit incomplete, right? There isn't complete data for all the processes. And so there were some intermediates that were dead ending that realistically, they would continue to be oxidized and produce species like formaldehyde, for example. So, we weren't the first to do this. When some of the Caltech reduced mechanisms were generated, they also did this, but we just had to expand this and ended up with our base mechanism, which we use as the ground truth, which has 428 species and 1,325 reactions. Okay. So a lot of people ask, okay, what approach did you use for reducing the mechanisms? Did you use machine learning? Okay, we've had a side project where we've worked with genetic algorithms to do that. We find that it's not as effective as the main approach we're using, which is based on graph theory. Okay, the idea is that we represent the chemical network as a directed graph, like a tree, right? And if any of you have been exposed to combustion research, this will look a little bit familiar. The kind of, we can think of atmospheric oxidation as combusting a fuel, right? And then you have many generations of oxidation products, and it's branching out into a tree. Here I've highlighted in blue, maybe this concept of priority species. So when I say a priority species, sometimes this is an end product. Like I mentioned, formaldehyde is something that that EPA is particularly interested in because they consider it an air toxic. It's a species that they want to control. So that would be an end product. But sometimes intermediates which may not be present in very large quantities, are important, for example, as secondary organic aerosol precursors, SOA precursors. So IEPOX might be one of those. And if we're just going by the logic of the algorithm, they might say, oh, the species isn't produced in that much mass, let's just delete it. But it's critical for the link to the other part of the model. So, we come up with this list of species, which we tell the model, you can't, cut this off from the rest of the network. Now, this is a cartoon of the mechanism. What the mechanism really looks like is this. Okay, it's a mess. And you can see the need for model reduction to get this simple and more manageable. All right. So in the first version of Amore, which was, it was specifically designed for the isoprene test case, we're using graph theory to investigate the paths in this graph and find which ones are the products most sensitive to. So which are the most important paths, and then those reaction paths are summarized and included in the final mechanism. If you want to find out more details about the algorithm, you can read the paper. We had to develop an error metric in order to test the models that we came up with at every stage. So it's just what it was. So comparing, whatever the reference is, looking at both the distance between those two results and the overall space covered, so normalizing it. Here's an example of what our results look like compared to other mechanisms and compared to experimental data. So this is experimental data from Caltech, where they had a chamber experiment for isoprene oxidation and showed IEPOX formation. So IEPOX is an important SOA precursor. And the green dots are the chamber data. Our model, the reduced Amore mechanism, which had 12 species, is lying here. The full-size Caltech mechanism with over 400 species is the blue one. Okay. And RACM2, which was the one of the default isoprene mechanisms in CMAC, is in the yellow line. So, we tested for many species. This is just an example, but in general, we're able to get quite accurate with a small mechanism using the Amore approach. Okay, so being a little bit more quantitative here, the Amore isoprene mechanism has 12 species and 22 reactions. It's similar in accuracy to the Caltech Reduce Plus mechanism, which is more than 10 times larger. It's similar in size to RACM2 and CBV6, but it's more accurate than those. Okay, so we managed to accomplish small size and high accuracy. So then we partnered with EPA to, it was a good coincidence that Havla Pai was developing CRACM, the next generation atmospheric chemistry mechanism for CMAC. And they found that their isoprene mechanism was kind of underperforming. And so around the same time, this is when we were developing Amore isoprene version 1, and they incorporated it into their new chemical mechanism. And we found that it improved agreement. So this is showing the CRACM without Amore and then CRACM with Amore all being run in CMAC. And then it's showing comparison to field observations, measurements made by EPA in the field of formaldehyde and ozone. And so and for every variable that we looked at, it either adding Amore either improved agreement or it didn't make it worse. It was roughly the same. So as a result, Amore is now incorporated in CRACM and is going to, it's one of the options that can be selected if you run CMAC. Okay. We also, several of the people on the team run GeosChem. Okay, so if you recall, the advantage with CMAC is that our mechanism is around the same size but more accurate. For Geochem, our mechanism is around the same accuracy but much smaller. And so basically the advantage is that we get a speed up for Geochem when we run Amore isoprene, the Amore isoprene mechanism. And this has been attractive, just speaking to a lot of Geochem users, maybe there are a few who are specifically focused on isoprene SOA chemistry, and so therefore they want all of the detail, but there are many who are not, they're focusing on something else. And so getting a little bit of speed up, with simplified chemistry, which will still have the accuracy, is very attractive to them. All right, so that's the published Amore version 1. Amore version 2 is underway. The things that we wanted to accomplish with this one is we want it to be general for any mechanism. That the version 1 was a little bit tailored to the isoprene case. So we're still using a graph theory approach, but it's slightly modified. And so far it's been applied to propane, furans, and camphene. And I would say one major difference is that Woods had to go in and optimize some of his coding because it was with a mechanism that's as large as camphene. It was a little too slow to run efficiently. So he's been working on things like that, but it's showing a lot of promise, especially for people who use automated mechanism generation. So tools like Gecko to generate their oxidation mechanisms. Then they can use Amore to reduce it to a more reasonable size for inclusion in large scale models. All right, so stay tuned for more developments on the Amore project. All right. Does anybody have any questions or anything? Before I jump to the second part of my talk?
No, I think we will come to the question and answer in the last.
Okay, I just wanted to pause a moment so that before I completely change channels here. All right, so in the last moments, I will share some work that's going on with the Clean Air Toolbox for Cities. This is an initiative that I'm leading at Columbia University as part of the climate school, and I'm leading it together with Dan Westervelt, who's from the Lamont Doherty Earth Observatory. So this is work we're doing across the global South, working directly with cities who are interested in moving towards cleaner air. And Dan is completely leading the work that we've done in Africa, which has been, very productive and extensive. And I've been more taking the overall leadership and leading the work that we're doing in India and elsewhere. This work we have a very highly interdisciplinary team at Columbia doing this work. So people from the law school, from the Mailman School of Public Health, climate school, engineering, public policy. But I would say that the strength of the program is actually our partners on the ground. So we have partners ranging from global organizations like WRI and EDF to local partners, including universities, government offices, grassroots organizations, nonprofits, etc. And we really, in all the work that we're doing, we put the people who are doing, kind of already active in the air quality space in the places where we're working, we put them front and center and have them leading on the projects that we work on. And then we're providing technical support. We think that this is the right way to do it, and it's been quite successful so far. So, everywhere we turn, we end up with very enthusiastic partners jumping on board, and it's been very exciting. Okay, so what do we actually do? Because we have such an interdisciplinary group at Columbia, we have a large variety of things that we can do to support the efforts. A lot of it does end up being data oriented, both because of Dan's and my expertise, but also because in many places, this is kind of the blocker towards progress is, either in Africa, many cases, there's no baseline air pollution measurement, so you can't start by saying, let's put a number to the problem and start to do the cost benefit analysis of cleaning up the air. Or later on, sometimes it's very, in India, it's very well known that there is an air pollution problem. There's active work on that. There's extensive measurements being done by the government, but there's still questions about, well, which sources are the most important ones to tackle? Where should we be investing our limited resources? So often the question is a data-oriented one, and us helping the people we're working with in removing that as a barrier. So much of what we're doing is involving smart application of low-cost sensor networks for air pollution, but we also do exposure monitoring, evaluation of specific air pollution interventions, source apportionment. We do work with satellite data and modeling. And then we have extensive work on the policy and legal side as well. All right. So, as an aerosol scientist, I was initially skeptical about low-cost PM sensing, but I've come to appreciate that if it's done right, it can be a very powerful tool. I used to say to myself, well, I've learned all the reasons why you need to use a scanning mobility particle sizer, for example, or you need a DMA with the CPC to really be able to detect particles, submicron particles. How can this little light scattering based instrument do the job, right? Why didn't I spend $200 for my SMPS when I first started my lab, if this really is all it takes? But the trick is designing your sensor network intelligently in such a way that you can get high quality data from these kind of lower value sensors. And the advantages is that they allow you to either expand monitoring beyond the coverage area of government monitors, can get higher resolution air pollution mapping, which one would hope would identify some hotspots to help point towards source identification. There are a lot of opportunities for indoor and outdoor comparisons, so informing exposure studies. And, in the case of what we're doing in Africa, it's a way to get started with sensing in low resource areas. Okay, so the big caveat, of course, is the physics of the issue. Low-cost sensor performance is sensitive to anything that would impact the aerosol optical properties, so temperature, relative humidity, and the sources of the particulate matter, which change seasonally, of course. There's also the issue of light scattering as a limitation for detecting particles that are less than 600 nanometers or so in size. And the way that we've dealt with this, and I think that it has been successful, is through calibrating our networks in the field on a cross-seasonal basis using reference grade monitors. Okay, so we had a paper published earlier this year in Aerosol and Air Quality Research on the first phase of our project in Kolkata. We also have an additional sensor network that was set up after this one, which I'll talk about now, which that work is forthcoming. But this is the first phase I want to talk about. This is a collaboration with a startup company that is in Kolkata, who had been funded by the World Bank to investigate the potential impacts of establishing an electric bus fleet there. Okay, so they got funding to set up a network of Clarity PM 2.5 sensors, and they set them up largely along two major bus routes, going north, south, and east, west in Kolkata, and then a few points of interest outside of those routes. And what I found very interesting and important about this data set was that they also co-located their clarity monitors with several reference grade monitors that were being run by a CPCB or the WBPCB. So I think they initially started out with 4 or 5 co-locations, but then a few of the sensors got stolen or destroyed. But they ended up with 3 decent co-locations at Victoria Memorial, Rabindra Bharati University, and Pudupukur, which is over in Howrah. Okay, so this is what the clarity sensor looks like. It has a solar panel. I would say that one of our recommendations at the end of the study is that clarity is not a good choice for the Indian context. I'm happy to talk about that offline, but this is what they used at the time when they established the network. This is an example of one of the co-location sites. So this is the RBU site where WBPCB has their reference grade monitor, their BAM, and they're very generous partners and allow us, and they also allowed Ideation Technologies to install their sensors at the same site so that we can directly compare measurements to the reference grade data. Okay, so this is what the raw data looked like for these 3 sites, and data were collected in kind of late 2018 and 2019, or early 2019, the first half of 2019. And the co-locations themselves, it took a few months to get all the paperwork and get everything established. So that data started in January, but it covers a good portion of winter and into the spring and maybe even the beginning of the monsoon. And you can see the the seasonality of pollution in Kolkata is, at least in the winter, it's kind of similar to other places in North India, very high PM 2.5 levels during the winter. I think that the air is a little bit cleaner in this after the winter compared to, say, Delhi in Kolkata because of a shift in the wind direction. So you have a very strong seasonality of the PM 2.5 there. This is the raw data, so this is just showing the agreement between the low-cost sensor and the reference grade monitor. It was not terrible at RBU and Pudupukur, but we did more with this to develop a calibration and get that agreement closer so that we could correct the whole data set and get high quality data. There's something going on at Victoria. I believe there might be an issue with the BAM there, or maybe environmentally it was just set up so that there would not be great performance for the sensor. We ended up not using this data for the rest of the analysis because the agreement was just a little bit unpredictable. But having 2 good co-location sites allowed us to do a lot and learn a lot. This is just the statistics for those 3 co-locations. You won't be able to read them right now, but you can read them in the paper if you're interested. We broke up the data, piecewise, looking at above and below 100 micrograms per meter cubed, which is essentially the same as making a seasonal cut, right? If almost the entire non-winter season is below 100 micrograms per meter cubed. And as others have done, we looked at the effect of relative humidity. Seems that PM 2.5 loading is more important. Excuse me. So what we did using those 2 co-location sites is we developed calibrations for the clarity and reference grade monitor pairs at those 2 sites. We used both random forest regression and multilinear regression. They both performed quite well, and so we moved forward with the multilinear regression because it actually produces an equation that makes it easier both intuitively to kind of share this information with people and then also easier to apply in our analysis to all the other sites in the network. Okay. Sorry for the strange things that happen with the font here. But what this is demonstrating is, the unique thing of having 2 co-locations in the same network is that it allowed us to test the the principle that we've all kind of accepted, that developing a calibration at a co-location is good enough, just one co-location, and then we can just apply it even if the other sites are kind of distant from it, right? And since we had 2 co-locations, we were able to test that. So using the equation that's developed at one of the sites, we could apply that to the raw data from the other site, get corrected data, and then compare that to the reference grade data there and see how accurate was this. And remember, RBU is quite far from Potapakur, which is actually in Howrah. And it seemed to be all right. So we, besides RMSE and these other statistics that we like to talk about as engineers, we tried to come up with other metrics that might be more meaningful for the WBPCB partners that we have. And so we calculated how accurate was the corrected data in diagnosing a day as being in or out of attainment, and it was the same as the reference grade monitor 91% of the time. And it was pretty good at assigning the right AQI category as well. Okay. So what ended up being a little bit unexpected and interesting was when we dug deeper into the data for all the individual sites and looked at the hourly variation in the data. Okay, so this is corrected data. Of course, there were like 20 sites. I'm not showing all of them here. You can see them in the paper. But this is showing representative months for each season that we were covering and what the hourly trends were like for those months. And I really expected that this data would be highly variable. So Howrah Depot, this is a bus depot, okay? RBU, you could see from that photo, it's in the center of a university campus, a little bit far from any major sources. Kamak Street is just like an urban area. And all of these places showed fairly similar trends, right? There weren't really any hotspots of note that we saw. There was kind of a typical maximum of PM 2.5 in the middle of the night during winter, corresponding to the boundary layer height shifting up and down. There was a little bit of a traffic bump during the rush hour in the morning and night for post-monsoon and winter. But then in the spring, interestingly, there was no traffic bump, for this giant city of Kolkata. And the maximum in PM 2.5 was coming in the afternoon. And so this is really typical for a situation where the sources of PM 2.5 are more photochemical, right? So secondary formation of particulate matter seems to be important in this case. Of course, we can't say what type of secondary particulate matter, whether it's SOA or there are power plants upstream of the city, maybe it has something to do with that. But this was quite unexpected. In fact, the reviewers didn't believe it. They said, how can it be you're in Kolkata, this city is choked with traffic, of course you should be seeing traffic peak. It's like, well, we're not, right? So even though there are a lot of assumptions about local sources being extremely important in a place where there are a lot of local sources, there's no doubt about that. When it comes to what's actually dominating the PM 2.5 signals, I think we need to get more data and think a little bit more carefully about that. The fact that there isn't a lot of variation from site to site across the city, even in sites that have different local sources, indicates that regional sources are important. And then this time trend suggests that secondary sources are also very important. And this is just showing that there's very high correlation among all the sites. This is kind of what I said qualitatively just now, that there wasn't a lot of variation from site to site. We can show this with a correlation coefficient that confirms that. And so besides the fact that this shows that regional sources are important and secondary sources may be important, it also kind of reinforces what we were saying, that it's appropriate to use a correction that was developed at RBU or PDM and apply it to the whole network. Okay. So I would say that this is, you know, there were kind of several levels on which I thought this study was interesting. You know, this last result I mentioned, which is giving hints about the important sources of PM 2.5 in Kolkata, that of course is there. But also simply, you know, this was a trust building exercise. You know, we've worked closely with WBPCB since 2019, having a lot of conversations, you know, trying to present the data in a way that, you know, really shows the value or lack of value of it. And, you know, over time, I think that their receptiveness to it has increased. And, you know, the study in general shows that there's some potential for using low-cost sensors to supplement the great work that's already being done by CPCB and WPCB and others to collect data across India. Right. So I'm done. I just wanted to give a little advertisement for the journal that I'm editor for, and I think many of you already publish with us. But ACS Earth and Space Chemistry, Atmospheric Chemistry, Aerosol Chemistry is certainly one of our focuses, and I encourage you to submit your papers to us, and I'll say thank you. I'll accept any questions you have.
Thank you. Now, Dr. Pandithurai will be taking care of the question answer session. Dr. Pandithurai.
Okay. Thank you, Professor Faye and McNeill, for an excellent talk. We have a couple of questions in the chat box. I will read out to you. Yeah, the first question is, are you able to hear?
Yeah, I can actually see the question in the chat. So the first one is from Subrata, right?
Yeah, Subrata Mukherjee. Yeah.
Okay. So the question, did you introduce any framework to estimate the isoprene SOA? I mean, this has been outside the scope of this project, right? We're focusing a lot of effort on working with the gas phase isoprene mechanism. We previously, gamma was essentially developed for this process, our model gamma. And of course, there are parameterizations in CMAC for isoprene SOA formation. So this is something that exists. It wasn't the focus of Amore, though.
Okay. There's one more question from in the chat box by Dr. Rakesh Kumar Mishra.
Okay. In metropolitan city, why is it important to make a tree garden area to make the air quality more fresh? Why is it important to simulate the air quality index for air quality control? And why is studying aerosols important? Okay, so I'll start with the second question. Simulating air quality is a very critical tool for air quality management. So here in the US, the model that I mentioned, CMAC, not only scientists use it to simulate atmospheric chemistry and air quality, also the, you know, so similar to what you have, we have the federal government and we have the state government. The federal government makes the standards, and then the states have to come up with a plan for how will they meet the standards. And the way that they show that they're going to meet the standard is by using the model, right? So they model different scenarios for how will the emissions go, how will the emission controls go, and then they can show if we do this, then we will succeed in meeting the standard, right? It's a very important tool to be able to predict. I mean, otherwise we're kind of doing random things and then hoping that the air quality will improve. But if you have some systematic way of testing the impact of your potential actions, then you can make smart decisions and make sure that they will have impact with minimal economic burden, right? So this is very important. It also is important for understanding how air quality will change as climate changes, for example, or other societal factors. So being able to simulate the air quality is essential. Tree gardens, You know, it's a mistake to say that just planting a tree, you clean the air. Like, no, that's not the case. There are cases where there may be a city that has a lot of dust storm problems, and having some kind of break of trees in between this source of dust and the city, that can help a little bit. But you know, I think socially we often think planting a tree, we overestimate the impact of doing that, right? And why is it important to study aerosols? You know, I think that I made that argument at the beginning, that it's not so obvious, you know, it's not simple, you know, I have a lot of, I think a lot about, for example, the clean air action plans that cities are putting together right now, trying to meet NCAP, right? And, you know, of course, they look around to what can they do within their grasp, right? So I can spray the road, I can make this person stop burning coal in the street, I can do this, you know, and that is what's within their control. But it's not so simple that we just control this source, control that source, and then the air will become clean. No, it's actually a lot of complex nonlinear processes that take us from the emissions that occur from human activities to the air pollution that we observe. And unless we understand aerosols, we can't make that connection. Okay. All right.
Thank you.
So I have some more questions here.
I see some hands raised. Dr. Manoranjan Sahu, you can ask your question.
Am I audible?
Yes.
Yes.
Yeah. So I have a couple of questions. So first of all, you talk about that reducing the models. So what are the key important features that should be considered while reducing the model from global scale to the regional scale? Because we are working in a very similar line. One of my PhD student is working on how to reduce basically the satellite data which are connected, which are collected over, around 50 kilometer to 100 kilometer resolution, how we can reduce down. This is one of the problem we are trying to address. So in that context, I'm asking, what are some of the key important features in your first principle model you are using so that you are able to get a very good, accurate prediction or the model results? This is number one. Number two is you discussed about the low-cost sensor and you deployed in Calcutta. And you also, although you got some good results, correlation around 0.8, and you mentioned that clarity sensors are not good for Indian conditions. And we have also very similar experience. We have deployed a lot of purple air sensors, okay, in Delhi as well as in Mumbai. I know there are some practical difficulties. I just wanted to know a little bit more about it. But just co-location is not enough. This is my understanding. We have already published several research papers on that, because relative humidity, temperature, the chemical composition of the aerosols, all these things changes from US to India. So something which has been calibrated for US cannot work really very well in India. So need to
That's exactly what my talk was about, was that we calibrated it in India. Yeah. Okay. So first part of what you were saying, you know, this kind of reduction that you're talking about is different from my topic.
Yes.
So you're talking about reducing satellite data. You know, our guiding principles were that we wanted to keep the structure, you know, the basic structure of the graph had to be intact, and that we were essentially doing a sensitivity analysis. So making sure that the components of the graph that the results were most sensitive to were retained. Okay. And then we did a lot of rigorous testing, comparing the results to anything we had available, whether it was the existing model or laboratory data or field data. So that, I mean, I guess that's the best answer I can give you. It's a different challenge from what you're describing.
So you are saying that you are reducing the model and then you are comparing with some ground truth data, right?
Yes.
Some ground
Many different forms of ground truth data. Yeah.
Correct. And then you are trying to say whether your model is, how good your model is predicting, correct?
Yes.
Right. Yeah. Okay. Oh, got it. Yeah.
And then, you know, you're correct that low-cost sensors are a challenge. Co-location by itself, that's not going to do much. And I've also seen people try to co-locate for like a couple days and then use a co-location that was just for a couple days and apply that, no, it has to be long-term over the seasons, right? Because the sources will change season to season. And then you have to use the collocation data intelligently to develop a correction, and it needs to be local. I don't, but I believe, I think we've seen that if you do this in the right way, you will get high enough quality data. Is it perfect? Is it the same as if you had a reference grade or research grade monitor? No, but there are enough other advantages of using the low cost sensor that it can be worth it if you do these things. Now the Clarity unit itself, issues, they're not that cheap. They have a data plan where you have to pay to get your own data. What else?
How much it costs?
I don't have the number off the top of my head. It was maybe around $1,000 per each one. It's not low. It's not what you would call low cost in any sense.
Okay.
I mean, it was a funded project. They, selected the sensor before I got involved. The advantage that Clarity had, at least at that time, was that they had a reputation for being more accurate than others.
Okay.
So back in 2018, 2019, people were using them quite a bit. I myself use a lot of purple air sensors. There's also disadvantages to using them. I would say that the perfect sensor doesn't exist for the Indian context yet. However, the ones that have this plan tower unit inside, on a technical level, they tend to perform better than others.
Okay.
Yeah.
Thank you.
Okay.
Thank you so much.
The next question is from Dr. Neeraj Rastogi.
Yeah. Okay. Thank you. So I have two questions. One is from your first part of your talk, and another one is from the second part. So from first part, means probably you explained, but I missed that part. You said that number of species and reactions, they were reduced by order of magnitude. So from
more than one order of magnitude, yeah.
And you are getting the similar results. So what is the concept? Means in algorithm, what has gone there? That means earlier, whatever if people are considering too many species or reactions, it is not necessary. Or means what is the concept? Means how it is getting reduced to 10, or can it reduce to be further few reactions? So I'm just trying to understand the concept. Means what is there?
Yeah, the idea is that we're summarizing the important parts of the mechanism and not representing parts that aren't impacting the results that we're focused on. It will depend on what you're focusing on, right? So let's say you're interested in some other intermediate species from us. It wouldn't be accurate for your application, probably. But yeah, when you look at this huge network, there are going to be parts of the network where there's not a lot of mass flowing through them, right? Those can be eliminated. Of course, if that's the only thing you're doing, you're just pruning this tree, then the accuracy goes down too much. So there's a point where you see like multi-step paths that need to be retained, but you can simplify them by summarizing the intermediate steps.
So will it be applicable to all the regions with different meteorological conditions or different emission sources? Some places, if you're over forest region, emission will be too much.
Right. I mean, that is the parameter space choice. That goes into your choice of the parameter space for developing the model.
Okay, thank you. And second question, I think many people are discussing about the same thing. It is related to low cost sensor network, which is growing very fast everywhere because of the reduced cost. But this is not question, I would say it is comment. Maintaining quality is really difficult. When you say initially when we are installing, we can have very good well calibrated sensors. But in long run, to make sure that quality is maintained over, if you are putting say 100 sensors at different places, one cannot have that much, reference monitor. So maintaining quality, I don't know, some way we have to find out that how to maintain the quality of the data. Obviously, it is not a question because you are working on that and many other people are working. Yeah, but
right. I mean, we in practice replace our sensors quite frequently. We don't trust the data after a certain point, right? And I think that expiration date is probably a little bit sooner in places with a higher loading, right? And I know people who specifically work on this problem, like, so how to tell if there's a drift in the sensors or a fault in one sensor or another sensor. Yeah, I think it's just part of the nature. And you know, if you end up having to buy a new low-cost sensor every 2 years, it's still cheaper than buying a BAM.
Yeah, but how do you know that your sensor has gone bad?
Well, I think that you can reasonably expect that after 2
Okay,
years,
some
for sure,
time
you
frame
need to
you
replace
expect.
it.
Okay,
Yeah.
yeah.
And people have done studies on this saying like, okay, this is the amount of time after which it will have degraded. But then there's also people, for example, I know there's some people at Microsoft Research doing like network research where they can tell one of the sensors is not behaving consistently anymore, and will help diagnose that. Like if you have access to the whole data dashboard.
So can high quality satellite data, means high resolution, high quality satellite data will be a means kind of, means if you have high quality satellite data, and that can be first validated with the low cost sensor because it has bigger network freshly installed. So means we can presume that their quality is good. So that way means either satellite data or low cost sensor, both are kind of calibrated, and time to time we can monitor. If once satellite data is calibrated, then means we can see whether it is matching with the satellite data or not. So we know that which part of sensor, means which region the sensor need calibration or things like that.
Yeah, I mean, usually the satellite data doesn't have the resolution that we need to really do that job, but that's a goal to have for sure.
Okay,
Yeah.
thank you. There are some questions in the chat. Some interesting questions in the chat you would like to see if you have time.
Right.
Yeah.
Well, I think we already discussed the drift of LCS data. I think the question from Subrata Mukherjee is about the change in air mass during the winter and summer. Yes, of course, that is why there's more pollution in the winter in Kolkata and less in April. What is meant by minimal information besides a full mechanism? What I mean is that we should not require an expert atmospheric chemist to have insights about the reaction network to designate what the important structure is going to be. We should be able to just say, these are our priority species, this is what the full mechanism is and what the kinetics are through the network. Please give me an accurate mechanism. Though if you're familiar with the way that model reduction normally goes, it's 100% expert insight. And maybe an organic chemist or somebody will assist, and it's almost like a bunch of magicians sitting around a table coming up with a reduced mechanism, and we don't, it shouldn't have to be like that. That's what I mean. Was the kinetic data already available? Yes. Well, I think some assumptions had to be made, but enough data were available. Can we rely on satellite-based monitoring of aerosols? I think that there's probably other people on the call who are more qualified than me to answer that question. Aerosols affecting climate, I agree. How can the study of aerosol chemistry help in that? I mean, we need to understand what the sources of particles are and what their physical chemical properties are that are important for climate, and those are all connected to aerosol chemistry. Is there any scientific progress in collecting LCS-based PM1? I don't really know the answer to that. I haven't looked into that. Mainly, I've been working on comparing to reference grade monitors from government data. Can I please suggest the best biogenic emissions estimates over India? No, I cannot. I'm sorry. I want to know too. Yeah. All right.
Yeah. Yeah. If there are no questions, I also have one question.
Okay.
So you mentioned that AMOR1, which deals mainly the isoprene.
Mm-hmm.
Only isoprene reactions and species relevant to that. Mm-hmm. But I think the Subrata was asking that whether any SOA estimations were made from the isoprene. So you said it's not implemented in AMOR V1, or it's not it's beyond the scope of this talk.
Right. I mean, so if you recall, I went a little bit fast through it, but we did incorporate Amore into CMAC and into Geoschem.
Okay.
And both CMAC and Geoschem already have isoprene SOA formation in them.
Okay.
Right. And so this connects to that part by, it's providing the estimate of IEPOX,
Okay.
for example, right? And then that is, how one of the major ways that SOA gets formed from isoprene.
Mhm.
So, we're kind of like leading up to that. And, of course, the SOA precursors were protected species in our mechanism. And then that feeds into whatever their isoprene SOA mechanism was. But we didn't touch that at this point.
Oh, so unless it gets into aerosols, so then it will not contribute to PM 2.5 or particulate matter pollution, right? When it's still in isoprene, it's in gaseous phase. So
no, I mean we implemented it into the large scale model, and then we compared the results to ambient measurements of PM 2.5 and all like that. Yeah.
Also, you mentioned that the reduction method is mainly. You said that AI or the deep learning method did not help much, and you mentioned that MOR V2 you introduced there is no manual intervention, or so it means
less
that
manual intervention.
Has some tuning which needs.
So what the first one, it got us, if you're running a race and then you get to the last little bit, right? It basically reduced the structure, but then it missed a few key things, like it missed some cycling of hawks and just the way that the algorithm was developed. And so, I mean, it was a matter of my student testing for 1 or 2 days and just tweaking it, and then it was ready, versus, what would have been months of hand tuning that was done previously. We wanted it to even not require that. We wanted it to be even more complete when the output came. So that was what was meant by that.
Okay, thank you. Are there any questions from audience?
Yes, sir. So, ma'am, you have just presented that you have worked on the low-cost sensors. So, I just wanted to know that what was the low-cost sensors expiration date in your case? That how much they last?
So this study that I just presented, it was less than a year's worth of data. It was a short-term study, and so performance seemed to be okay over that time period. In other experiences we have with the Purple Air, we're still looking at our data. Based on what the community does, I'm not looking at more than 2 years worth of data from the sensors that we have. But I don't have the statistics yet for whether it was starting to degrade before that or not.
Okay, so in the clarity sensor that you are using, so is there any company that provided that how much there is laser sources or any sensor is degrading, at which rate they are degrading?
The project with Clarity ended only after, I don't know, it was 8 months or 9 months, something like that. And so it wasn't an issue. I don't know if currently Clarity offers that as an analytical tool or not. I don't use Clarity at this point.
No, but in my case, that in my sense that whatever the data that local sensor measures, the majority issues